Hey guys, welcome to this new story. Today, we set our sights on the largest planet in our solar system and the strange, burning eye that has stared back at us for centuries. On the surface of Jupiter swirls the Great Red Spot, a storm so massive that Earth itself could fit inside it. First seen through early telescopes more than 300 years ago, this giant storm has never truly faded. Its clouds spin at hundreds of miles per hour. Its colors shift from deep brick red to pale orange, and its size slowly changes as if the planet itself is breathing. But what is this red eye really? Why has it survived while storms on Earth die within days? What powers it in the freezing darkness, so far from the sun, beneath those thick bands of gas? Powerful winds crash into each other. Heat rises from deep within the planet, and forces we are only beginning to understand keep the storm alive. In this video, we journey into Jupiter's turbulent skies to uncover the truth behind its most famous feature and reveal what this endless storm teaches us about how giant worlds work. Jupiter is the largest planet in the solar system. Its size alone defines much of its influence on nearby space. With a diameter of nearly 143,000 kilometers, it stretches across more than 11 Earths placed side by side. Its mass is greater than all the other planets combined, creating a gravitational pull that shapes the orbits of surrounding moons, rings, and even smaller objects such as comets and asteroids. This gravity also compresses its interior, producing pressures and temperatures far beyond those found on Earth. Jupiter is primarily composed of hydrogen and helium, the same elements that dominate the Sun. The hydrogen exists in multiple forms, from molecular gas in the upper atmosphere to metallic hydrogen deep inside the planet. Helium makes up a smaller fraction, contributing to the overall density and affecting energy transport. Trace compounds like methane, ammonia, water, and complex hydrocarbons are dispersed throughout the layers, each participating in chemical reactions under extreme pressures and temperatures. The planet's atmosphere is divided into several layers. The visible clouds form the top layer of the troposphere, a region defined by vertical movement and convection. Below this, pressure increases rapidly, and temperatures rise with depth. In the middle layers, hydrogen transitions from a gaseous to a liquid state under intense pressure. Deeper still, at pressures millions of times higher than Earth's atmosphere, hydrogen adopts a metallic state, conducting electricity and generating Jupiter's powerful magnetic field. The transition between these layers is gradual, with no solid surface as found on terrestrial planets. Jupiter's internal heat is significant. The planet emits nearly twice as much energy as it receives from the Sun. This heat originates from gravitational contraction and the slow settling of helium within the interior. Convection transports this heat outward, driving atmospheric motion and contributing to the formation of large-scale storms. Jupiter rotates rapidly, completing a full rotation in just under 10 hours. This fast rotation causes the planet to bulge at the equator, producing an oblate shape. It also drives powerful zonal winds in the atmosphere, dividing the planet into distinct bands. These bands alternate between lighter zones and darker belts, corresponding to differences in chemical composition, temperature, and wind direction. Each band hosts its own circulation patterns, with high-speed jets reaching hundreds of kilometers per hour. The interaction of these jets forms boundaries where turbulence concentrates, providing the conditions necessary for long-lived storms. Among the many features in Jupiter's atmosphere, the Great Red Spot is the most prominent. Before focusing on the red spot itself, it is essential to understand the general storm dynamics. The planet hosts thousands of smaller vortices, ranging from compact white ovals to larger brown features. Storms form where energy from the interior combines with the shear of adjacent jet streams. Rising and sinking gases carry heat, chemical compounds, and momentum across the atmosphere. Storms can merge, split, or change shape over time. The rotation of Jupiter stretches these storms along the east west axis, allowing them to maintain coherence for extended periods. The composition of Jupiter's atmosphere affects the color, density, and structure of these storms. Ammonia clouds form high in the atmosphere, appearing as white or pale regions. Below these, compounds such as ammonium hydrosulfide create brownish tones, while the presence of complex hydrocarbons may contribute to red hues. The distribution of these chemicals varies with latitude, altitude, and time. Chemical reactions can occur under sunlight in the upper layers or under pressure and heat deeper down. These reactions release energy, contribute to convection, and modify the appearance of clouds. Jupiter's gravity plays a central role in the behavior of its atmosphere. The planet's strong pull compresses the gas layers, increasing density and pressure with depth. This compression enhances convection, drawing heat upward and powering jet streams. Gravitational interactions also stabilize large storms, preventing them from dissipating as quickly as on smaller planets. The depth of the atmosphere allows for vertical circulation patterns that can extend thousands of kilometers below the visible clouds. These patterns influence both temperature and wind velocity at the surface, creating a three-dimensional structure that is continually in motion. Observations of Jupiter have been conducted over decades using telescopes on Earth and spacecraft sent to study the planet. Space missions such as Pioneer, Voyager, Galileo, and Juno have provided detailed measurements of atmospheric composition, pressure, temperature, and magnetic fields. Remote sensing techniques, including spectroscopy, infrared, imaging, and radio wave analysis, allow scientists to probe layers below the visible clouds. These observations confirm that Jupiter's atmosphere is both dynamic and complex, with interactions between chemistry, physics, and rotation producing the large-scale patterns visible from afar. The scale of Jupiter's features is immense. Even modest storms on this planet exceed the size of Earth. The Great Red Spot alone spans tens of thousands of kilometers. Smaller vortices, while comparatively minor, still dwarf terrestrial hurricanes. The vast size of the atmosphere allows for long-term energy storage. Storms can survive for years or centuries because there is sufficient space and pressure to maintain circulation. Unlike Earth, where friction with the surface limits storm longevity, Jupiter's lack of a solid surface means storms persist with minimal interference. Energy transport within Jupiter occurs through a combination of radiation and convection. Solar energy is absorbed at the upper layers, heating clouds and driving chemical reactions. Internal heat rises from the deep interior, moving upward through turbulent convection. This combination fuels atmospheric dynamics, including the formation of storms and maintenance of zonal bands. Convective cells bring material from lower layers to the upper atmosphere, altering cloud composition and cloud color. Temperature variations between the equator and poles influence circulation, contributing to the planet's complex wind patterns. The interaction between chemical composition and physical motion shapes the overall appearance of Jupiter. Lighter zones correspond to rising ammonia clouds, while darker belts contain descending material mixed with chemical byproducts. Storms form where these zones meet, creating eddies and vortices of varying size. The persistence of storms is a product of both chemical stability and mechanical reinforcement from surrounding wind patterns. Even transient features provide insight into atmospheric processes, revealing the interaction between convection, rotation, and chemical layering. As the largest planet in the solar system, Jupiter's influence extends beyond its immediate atmosphere. Its gravity affects moons, rings, and minor bodies, shaping orbital paths and driving tidal heating in certain satellites. The planet's magnetic field, generated by metallic hydrogen deep within, interacts with charged particles in space, producing auroras at the poles. These interactions are visible from both spacecraft and telescopes, offering additional data on atmospheric composition, energy flows, and magnetic properties. Jupiter's observable features are only the surface expression of deeper processes. Beneath the clouds, pressure increases steadily and temperatures rise. Hydrogen transitions into a metallic form capable of conducting electricity, fueling the planet's magnetosphere. Helium separates partially from hydrogen under these conditions, forming droplets that sink toward the interior, releasing additional heat. These internal movements contribute indirectly to atmospheric dynamics by sustaining convection and providing continuous energy to the visible cloud layers. The rotation of Jupiter further influences the structure of its storms. Fast rotation stretches storms longitudinally, creating elongated vortices. Shear between adjacent jet streams concentrates turbulence, producing boundaries that stabilize large storms. Coriolis forces deflect rising and falling gases, reinforcing circular motion. This combination of effects allows the Great Red Spot and other long-lived storms to maintain their structure over centuries, despite the constant flow of material in and out of the system. Jupiter's upper atmosphere is shaped by both chemistry and solar influence. Ultraviolet light from the sun initiates reactions in ammonia and methane, producing complex organic molecules. These compounds contribute to the coloration of clouds, especially in the upper layers. Seasonal and diurnal variations in sunlight slightly alter temperature and chemistry, modifying cloud opacity and cloud tone. Though small compared to internal heat, solar input is sufficient to drive chemical reactions that influence appearance at the visible surface. Measurements of wind speeds reveal intense motion within Jupiter's atmosphere. Equatorial jet streams reach velocities exceeding 100 meters per second, while localized storms exhibit winds surpassing 400 kilometers per hour. The magnitude and distribution of these winds vary with latitude and depth, influenced by both planetary rotation and energy transfer from the interior. Vertical wind profiles indicate rising currents within storm centers and descending motion along edges, forming a continuous cycle of convection. Chemical tracers such as ammonia, water vapor, and hydrocarbons serve as markers for atmospheric circulation. Clouds composed of ammonia ice indicate regions of upwelling, while darker belts with mixed compounds correspond to descending air. Spectroscopic analysis allows scientists to map these tracers in 3 dimensions, revealing complex interactions between chemistry and motion. Seasonal, solar, and stochastic variations further modify these patterns, producing a constantly evolving but structured atmosphere. The scale of Jupiter's atmosphere provides a laboratory for studying physics in extreme conditions. Pressure, temperature, and chemical gradients exceed those found on any terrestrial planet. Storms, vortices, and jet streams operate on dimensions and energy scales that cannot be replicated on Earth. Observing and modeling these features yields insight into fluid dynamics, convection, and chemical interactions under high-pressure hydrogen-helium environments. Observational history highlights long-term trends. The Great Red Spot has persisted for centuries, shrinking gradually over time but maintaining overall stability. Smaller storms appear and vanish, merging into larger vortices or dissipating due to shear. These patterns reflect the balance between energy input from the interior, solar radiation, and mechanical stabilization by surrounding flows. Long-term monitoring provides essential data on planetary evolution and atmospheric physics. Jupiter's overall structure demonstrates the relationship between size, composition, and atmospheric dynamics. Its immense gravity creates pressure gradients that drive convection. Its rapid rotation produces banded wind patterns, and its chemical makeup interacts with light and heat to produce visible clouds. Every observed storm, jet stream, and cloud layer is a consequence of these interacting factors, providing a window into processes that govern not only Jupiter, but potentially other gas giants in the universe. The planet's magnetic field generated by the metallic hydrogen interior, interacts with atmospheric ions, producing currents that influence storm formation. Charged particles follow field lines, creating auroras and electrical currents that extend above the visible clouds. These electromagnetic interactions affect ionized compounds in the upper atmosphere, subtly altering chemistry and cloud properties over time. Jupiter's moons also interact gravitationally with the planet. Tidal forces from moons like Io and Europa transfer energy into the planet's interior and indirectly into the atmosphere. These forces contribute to convection patterns, influencing the distribution of heat and momentum. Observations of the planet moon system provide context for understanding how external forces affect atmospheric dynamics and storm stability. The combination of internal heat, rotation, chemical composition, and gravitational influence results in an atmosphere that is both structured and dynamic. Storms form where conditions favor upwelling and circulation. Jets organize into alternating bands, and chemical interactions modify visible properties. These features are interdependent, creating a system that evolves gradually while maintaining long term patterns. The atmosphere of Jupiter extends thousands of kilometers above the invisible boundary, where gases gradually merge with space. The top layer, known as the exosphere, contains extremely thin gas. Particles are spaced widely apart, and the density is low enough that molecules can escape into space. Below this, the thermosphere begins, where temperatures rise as sunlight and charged particles deposit energy. In this layer, hydrogen and helium dominate, and some ionization occurs. Electrons and ions interact with the planet's magnetic field, producing currents that can flow along field lines. Energy absorbed here contributes only slightly to the movement of the lower atmosphere, yet it shapes the upper limits of the gaseous envelope. The stratosphere lies beneath the thermosphere, extending downward toward the visible cloud. Layers. Here, the air is stable, with less vertical mixing compared to the troposphere below. Temperatures in the stratosphere are generally moderate, increasing slightly with altitude due to absorption of ultraviolet light. Photochemical reactions occur in this region, breaking down methane and other trace gases under solar ultraviolet radiation. These reactions form compounds such as ethane, acetylene, and other hydrocarbons. Some of these molecules rise to higher layers, contributing to haze formation. The stratosphere acts as a buffer, separating the turbulent lower layers from the more diffuse upper atmosphere. The troposphere is the thickest and most active portion of Jupiter's atmosphere. It contains the clouds visible from telescopes and spacecraft, forming a dynamic layer where convection dominates. Rising gas carries heat from the deep interior toward the surface, while cooler gas descends, creating circulating cells. The pressure here increases rapidly with depth, near the visible cloud tops. Pressures are roughly 1 bar, similar to Earth's surface, but a few kilometers below, the pressure climbs to tens or hundreds of bars. Temperature also rises with depth, starting at about minus 140 degrees Celsius near the upper clouds and exceeding hundreds of degrees deeper down. Cloud formation in the troposphere depends on chemical composition. Ammonia condenses at the highest altitudes, forming white clouds that often appear as patches or bands. Below these clouds, ammonium hydrosulfide can condense, producing darker brown or reddish tones. Deeper still, water vapor forms clouds that can be thick and dense, though these are rarely visible from above. Each layer is layered vertically, with rising gas passing through one condensation level after another, carrying particles upward and mixing chemicals as it ascends. This layering affects color, opacity, and storm development. Hydrogen and helium dominate the bulk of the atmosphere, making up more than 99% of all molecules. Hydrogen exists mostly as a molecular gas in the upper layers, but begins to transition into liquid and metallic forms under the immense pressure below the cloud tops. Helium, though less abundant, is heavier and can separate from hydrogen under certain conditions, forming droplets that fall toward the interior. The distribution of these gases influences density, pressure gradients, and the movement of energy through convection. Trace compounds also shape atmospheric behavior. Methane absorbs sunlight and participates in chemical reactions that produce more complex molecules. Ammonia interacts with water and other gases to form cloud particles. Water vapor is an important carrier of heat. It condenses and releases latent heat, powering upward motion. Each compound responds differently to pressure and temperature, creating vertical zones where chemical interactions dominate. The interplay of gases establishes temperature gradients that define the structure of the troposphere. Temperature in Jupiter's atmosphere is not uniform. It varies with altitude, latitude, and local circulation patterns. The equatorial region tends to be slightly warmer than higher latitudes due to the concentration of sunlight and internal energy flow. Vertical motion carries heat upward from the interior, and large storms redistribute energy across horizontal distances. In some regions, convective plumes can carry warmer gas high into the atmosphere, forming elongated clouds and contributing to the visible banding. Cooler air descends along belts, thus stabilizing layers and creating contrasts in cloud brightness. Pressure increases steadily with depth, creating conditions unlike those on terrestrial planets. At 10 bars, gas behaves more like a dense fluid than the thin atmosphere near the cloud tops. At hundreds of bars, hydrogen compresses into liquid and begins to influence magnetic fields. This gradient controls the vertical gradient, controls the circulation of gases, and helps sustain long-lived vortices such as the Great Red Spot. The combination of high pressure and varying composition allows for multiple cloud layers to coexist while maintaining vertical motion and chemical exchange. Ammonia clouds dominate the upper troposphere, forming thin sheets that drift along jet streams. Their density varies with temperature and vertical movement. Below them, ammonium hydrosulfide clouds appear as darker, thicker layers. The chemical reactions producing these clouds are sensitive to pressure and temperature, causing variations in cloud height and thickness. Deep water clouds are less uniform, influenced by convection and localized upwelling. The layering of clouds produces the characteristic striped appearance of Jupiter's bands. Hydrogen, helium, and trace gases interact constantly in these layers. Rising parcels of gas carry compounds upward, where low temperatures allow condensation. Descending air returns heat to deeper layers. This convective cycling sustains atmospheric circulation and affects wind patterns. The vertical structure, combined with rotation, produces the alternating zones and belts that define the planet's appearance. Jet streams follow these bands, often reaching hundreds of kilometers per hour. Their direction alternates with latitude, forming a structured but constantly moving pattern. Chemical interactions in the atmosphere are influenced by both solar radiation and internal heat. Ultraviolet light breaks down methane, forming hydrocarbons that can rise to form haze. Solar heating in the stratosphere slightly increases temperature, supporting photochemistry. Internal heat drives convection, bringing material from lower layers upward. The combination of these energy sources allows compounds to circulate vertically and horizontally, modifying cloud composition and color. The deep atmosphere remains largely inaccessible, but can be inferred from models and measurements. As pressure rises, molecular hydrogen begins to behave as a dense fluid, and metallic hydrogen forms at extreme depths. These layers are hotter and more conductive, influencing the magnetic field and indirectly affecting the troposphere above. Convection draws energy from the deep interior, fueling storms and circulation. The movement of gases through various chemical zones shapes the visible atmosphere, linking processes occurring kilometers below the cloud tops to the patterns seen from afar. Ammonia, methane, and water play specific roles in atmospheric dynamics. Ammonia condenses high in the troposphere, creating reflective clouds. Methane absorbs and re-emits energy, Influencing temperature distribution, water condenses at lower altitudes, releasing heat that powers upwelling currents. The combination of these compounds defines cloud opacity, banding, and the structure of storms. Chemical layering ensures that each element contributes at specific levels, producing observable effects without interfering with deeper processes. The stratosphere, thermosphere, and exosphere each contribute to the overall atmosphere while remaining distinct. The troposphere houses visible clouds, convection, and the majority of chemical reactions relevant to storm formation. The stratosphere provides stability and acts as a transitional layer. The thermosphere responds to sunlight and magnetic interactions, while the exosphere forms the outer boundary with space. Together, these layers create a complex system governed by physics, chemistry, and planetary rotation. Jupiter's atmosphere is a system of layers, circulation, and chemical processes. Each layer interacts with the others, transferring heat, gases, and energy. Convection brings compounds upward, gravity drives pressure gradients, and rotation organizes movement into bands. The presence of ammonia, methane, water, and other trace compounds establishes cloud formation and visible coloration. Hydrogen and helium dominate mass, yet the interplay of minor compounds defines observable patterns. This combination produces the dynamic, layered, and chemically active atmosphere that envelops the largest planet in the solar system. Jupiter's atmosphere is marked by a series of alternating light and dark bands. These bands run roughly parallel to the planet's equator and stretch thousands of kilometers across. The lighter bands are called zones, while the darker bands are known as belts. Each band corresponds to a different circulation pattern. Zones are generally regions where gas rises, cools, and forms high, bright clouds. Belts are areas where gas sinks, warming as it descends, creating darker clouds. The contrast between these bands is caused by differences in chemical composition, temperature, and cloud density. The boundaries between belts and zones are areas of strong wind shear, where the horizontal movement of gases changes rapidly. Within and between these bands, high-speed jet streams dominate atmospheric motion. Jet streams are narrow, fast-moving rivers of gas flowing primarily east or west. Some jets reach speeds of over 400 kilometers per hour. The number, speed, and direction of these jets vary with latitude, producing a complex network of moving currents. Adjacent jets often flow in opposite directions, creating sharp gradients that concentrate turbulence and influence storm formation. These jets are powered by the combination of internal heat rising from the planet's interior and the rapid rotation of the planet, which redistributes momentum across latitudes. Storms form in regions where these bands interact, especially at the boundaries between zones and belts. Rising warm gas from the interior encounters descending cooler gas, creating vortices that rotate around a central point. Coriolis forces caused by Jupiter's fast rotation bend these flows into circular or oval shapes. Smaller vortices can merge over time to form larger, more stable storms. Each storm is a self-contained system of rising and descending gas, drawing energy from the surrounding jet streams. The shape and size of a storm depend on the balance between the internal energy driving convection and the stabilizing forces provided by the surrounding flows. Vortices on Jupiter range widely in size. Some are as small as a few hundred kilometers, while the largest, like the Great Red Spot, can exceed 20,000 kilometers in width. Despite the size of the planet, the rapid rotation stretches these storms east-west, producing elongated or oval shapes rather than circular ones. Smaller storms often move within the banded structure, merging with other vortices or dissipating over time. The longevity of a storm depends on the availability of energy from rising gas, the absence of strong disruptive forces, and the stability of surrounding jet streams. Zonal flows play a critical role in maintaining the structure of Jupiter's atmosphere. These flows are the east west winds that define belts and zones, producing the banded appearance visible from space. Within a zone, rising gas moves slowly relative to the surrounding currents, while belts feature faster downward moving air. The alternating directions of adjacent jets create shear zones, regions of high turbulence, where energy is concentrated. These regions can generate new storms or reinforce existing ones, allowing large vortices to survive for decades or even centuries. The correlation between Jupiter's rotation speed and atmospheric turbulence is pronounced. The planet completes a full rotation in under 10 hours, which is rapid for its size. This fast rotation generates strong Coriolis forces, deflecting moving gas and stabilizing circular flows. The rotation also elongates vortices along the east west axis, preventing them from collapsing under their own turbulence. As a result, Jupiter can sustain storms that are far larger and longer lived than those on Earth. Rapid rotation influences jet formation, determines the spacing of belts and zones, and affects the intensity of turbulence across latitudes. Energy from the planet's interior feeds atmospheric motion. Convection brings heat upward, creating rising columns of warm gas that expand into the troposphere. These columns encounter horizontal jet streams, which shear the rising material into elongated storms. Descending cooler gas completes the circulation, releasing heat deeper within the planet. The interplay of rising and falling gas, combined with horizontal wind shear, establishes a continuous cycle that drives storms, shapes cloud patterns, and redistributes energy across latitudes. Smaller storms often appear as white or brown ovals. White ovals form where ammonia clouds condense in rising columns of air, while brown ovals are composed of descending, chemically altered gas. These features can drift along jet streams, collide with other storms, or merge into larger systems. Observations indicate that white ovals can persist for decades, slowly shifting in size and shape, while brown ovals sometimes disappear after a few years. The combination of storm size, surrounding flow, and chemical composition determines how long each feature remains active. Large-scale turbulence arises when multiple storms interact with zonal flows. Collisions between vortices can stretch, twist, or compress storms. Energy is transferred from one storm to another, producing oscillations and waves in the surrounding atmosphere. Even distant jet streams can influence the development of storms, as momentum carried across belts and zones affects the rotation and drift of vortices. This dynamic system maintains both structure and variability in Jupiter's atmosphere. The Great Red Spot is a prime example of these dynamics. It sits between two strong east-west jets, which help stabilize its position. Rising gas from the interior circulates within the storm, maintaining its size and rotation. Surrounding turbulence and smaller storms and chemical layering contribute to the overall structure, while Coriolis forces preserve the oval shape. The combination of rotation, convection, and shear allows this storm to persist far longer than any on Earth, illustrating how Jupiter's unique atmospheric dynamics sustain extraordinary features. Observations from spacecraft and telescopes reveal that storms influence atmospheric bands. Rising plumes can temporarily brighten zones, while sinking air darkens belts. Jet streams distribute clouds, heat, and chemical compounds across vast distances. Even minor turbulence in one area can create ripples that affect regions thousands of kilometers away. Storms are not isolated events. They are part of a larger system of moving gases shaped by rotation, convection, and chemical interactions. The interaction between rotation and turbulence can produce secondary features, such as waves or smaller eddies around large storms. These secondary features carry momentum and heat, subtly influencing the main storm's energy balance. The result is a multi-layered system in which energy moves in several directions, producing patterns that are both stable and dynamic. Observations of these interactions provide insight into the physical laws governing fluid dynamics under extreme conditions. Wind speeds, rotation, and convection combine to produce the distinctive striped appearance of Jupiter. Zones and belts are maintained by rising and falling gas, alternating wind direction, and chemical contrasts. Storms are embedded within this pattern, forming and persisting where energy is concentrated. High speed jets, combined with Coriolis forces, allow vortices to rotate for years without losing coherence. The organization of bands, jets, and storms demonstrates how physical forces create predictable patterns amid constant motion. Energy exchange in the atmosphere continues over long timescales. Internal heat drives convection, feeding rising columns and vortices. Horizontal wind shear redistributes momentum, shaping the banded structure. Solar radiation contributes to photochemical processes affecting upper clouds. The combination of forces produces a self sustaining system in which storms appear, interact, and occasionally dissipate, while the overall circulation remains organized. Storm formation depends on vertical stability, available energy, and the surrounding flow. Rising warm gas forms a vortex, which is then shaped by east-west winds and Coriolis forces. As the storm develops, it interacts with nearby jets and other vortices. Shear zones reinforce the edges of storms, preventing them from dispersing quickly. The result is a variety of storm types, ranging from transient white ovals to massive, long-lived features, like the Great Red Spot. The longevity of storms is also linked to the depth of the atmosphere. Jupiter has no solid surface to impede motion. Rising and sinking gases can circulate freely for thousands of kilometers. The depth of the troposphere allows energy to be stored over long distances, giving storms the fuel to persist for years. Internal heat, combined with rotation and chemical composition, creates conditions where large storms can remain stable despite constant turbulence around them. Even in regions without major storms, turbulence is present. Small vortices, eddies, and waves constantly move within belts and zones. These smaller features transfer energy to larger storms or dissipate it gradually. The atmosphere is never static. Every region participates in a dynamic balance that maintains the overall structure while allowing local variability. Jupiter's high-speed winds, zonal flows, and storm interactions reveal the link between planetary rotation and atmospheric complexity. Rapid rotation elongates storms, creates strong shear zones, and generates Coriolis forces that preserve circulation. Convection powered by internal heat drives vertical motion, which interacts with horizontal jets to produce vortices. Chemical layering and cloud formation provide visible evidence of these processes. Together, these factors define the planet's storm systems and their long-term behavior. The Great Red Spot is the most well-known storm on Jupiter, easily visible from Earth with the aid of telescopes. Its discovery dates back to the 17th century, when astronomers first noted a persistent reddish feature in the southern hemisphere of the planet. Over the centuries, observers recorded its position, shape, and color, creating a historical timeline of its presence. Early drawings show a large oval feature, though details were limited by the resolution of instruments at the time. These records provide insight into how long the storm has persisted and how its appearance has changed over the years. Historical observations indicate that the size of the Great Red Spot has varied. In the 19th century, measurements suggested a length of more than 40,000 kilometers, wide enough to span across multiple Earths. Over time, the storm has gradually contracted. Modern measurements indicate a width closer to 16,000 kilometers, though it remains the largest vortex in the solar system. The contraction is not uniform. The storm maintains an elongated oval shape, stretched east-west by Jupiter's rapid rotation. Changes in length and width have been tracked using photographic plates, digital imaging and space based instruments. Color variations have also been documented. The storm's reddish hue can appear deep and intense, or lighter and more muted depending on observational conditions and atmospheric chemistry. Spectroscopic studies reveal that the coloration is influenced by compounds in the clouds, including complex hydrocarbons, phosphorus compounds, and possibly sulfur. Over time, shifts in cloud composition, altitude, and the intensity of solar radiation can alter the observed color. Ground based and space based instruments help scientists quantify these changes using consistent wavelength measurements to detect subtle differences. Intensity of the storm, measured by wind speed and rotational energy, has also fluctuated. Wind speeds at the edges can exceed 400 kilometers per hour, while the central region rotates more slowly. Observations indicate that rotational energy has varied, with periods of relative stability followed by temporary weakening or strengthening. Tracking these changes helps scientists understand how energy is supplied to the storm and how it interacts with surrounding atmospheric flows. Observations of the Great Red Spot have improved significantly with modern technology. The Hubble Space Telescope provides high resolution imaging from orbit, capturing cloud patterns, color variations, and motion over time. Juno, in orbit around Jupiter since 2016, delivers close up measurements of atmospheric composition, wind velocity, and temperature profiles. Instruments on Juno can observe the storm from multiple angles, including infrared sensors that detect heat and microwaves that probe deeper into cloud layers. These data complement long term observations from Earth based telescopes, providing a continuous record of the storm's behavior. Measuring the size and rotation of the Great Red Spot presents challenges. Jupiter's rapid rotation, about once every 10 hours, causes differential movement across latitudes, making it difficult to track features accurately. Storm edges are diffuse, blending gradually into surrounding clouds, which complicates precise boundary determination. Changes in cloud opacity and lighting also affect apparent size and color. Researchers rely on multiple imaging techniques, including time-lapse photography, spectral analysis, and cross-referencing measurements from different instruments to achieve consistent results. Historical tracking relied on drawings, notes, and early telescopic images. Astronomers compared positions relative to known latitudes and longitudes, estimating rotation periods and drift rates. These methods, though approximate, provide valuable long-term data on the storm's persistence. Modern digital imaging allows precise measurement of cloud motion and wind speed using pixel tracking and automated algorithms. Combining historical records with contemporary data offers a comprehensive view of the storm's evolution over centuries. The storm's location is relatively stable, situated in Jupiter's southern hemisphere at roughly 22 degrees latitude. It drifts slowly over time, influenced by nearby jet streams and surrounding vortices. The position has been mapped continuously, revealing subtle east-west and north-south shifts. These movements are linked to interactions with smaller storms and waves in the surrounding atmosphere. Understanding positional changes helps scientists model the forces maintaining the storm's longevity and the constraints imposed by Jupiter's zonal flows. Changes in color and intensity often correlate with atmospheric composition. Spectroscopic data show that cloud-top chemicals such as complex hydrocarbons, ammonia, and phosphorus compounds are unevenly distributed within the storm. These compounds interact with sunlight, creating variations in color and brightness. Temperature differences also influence visible features, as rising warm gas may bring compounds to higher altitudes, enhancing coloration. Infrared observations from space-based telescopes reveal heat patterns that indicate how energy circulates within the storm. Monitoring the Great Red Spot requires careful calibration over time. Differences in instrumentation, observation conditions, and data processing can create apparent changes that are not due to the storm itself. Scientists standardize measurements using reference features, consistent imaging wavelengths, and repeated observations over multiple rotations of Jupiter. Data from Hubble, Juno, and ground based telescopes are combined to produce continuous time series that reveal trends in size, shape, color, and wind speed. This approach allows researchers to track both short term fluctuations and long term changes. The longevity of the storm is a topic of particular interest. Centuries of observation confirm that it is the largest, most persistent storm in the solar system. Analysis of historical records indicates that it has survived despite gradual changes in size and shape, influenced by surrounding atmospheric flows. Modern measurements show a trend of slow contraction, yet the overall structure remains stable. Understanding the factors that allow such long term persistence informs models of fluid dynamics, atmospheric stability, and energy transport on gas giants. Instruments aboard spacecraft like Juno provide three-dimensional insight into the storm. Microwaves penetrate the cloud tops, revealing deeper structure. Infrared sensors measure temperature differences across the storm. High-resolution cameras track individual cloud motions, allowing scientists to map wind vectors and rotation rates. Combining these measurements with data on chemical composition gives a detailed picture of how the storm functions as a self-sustaining system within Jupiter's turbulent atmosphere. Ground-based observations complement space missions. Observatories equipped with adaptive optics and spectrographs can resolve cloud details, measure rotation periods, and detect subtle color shifts. Long-term monitoring from Earth provides context for short-duration spacecraft observations. By comparing data over decades, scientists can identify trends such as gradual contraction or color changes that might otherwise be overlooked. Tracking cloud motion involves measuring the displacement of individual features over time. Wind speed is inferred by calculating how far clouds move relative to Jupiter's rotation. Repeated measurements allow scientists to determine the circulation pattern within the storm, revealing the distribution of kinetic energy and the strength of rotational motion. These techniques require careful consideration of viewing angle, planetary rotation, and cloud opacity. Despite centuries of observation, challenges remain. Jupiter's rapid rotation, thick atmosphere, and diffused cloud edges make precise measurements difficult. Cloud features change shape continuously, adding uncertainty. Variations in lighting and observational conditions can affect perceived color and brightness. Scientists use multiple methods and repeated observations to reduce these uncertainties and ensure that trends reflect real changes in the storm rather than observational artifacts. The combination of historical and modern data provides a comprehensive understanding of the Great Red Spot. Centuries of tracking reveal long-term trends in size, color, and intensity. High-resolution observations from space missions provide detailed measurements of wind speed, chemical composition, and temperature. Together, these data allow scientists to model the storm's structure, circulation, and interaction with surrounding atmospheric flows. Understanding these factors offers insight into the persistence and evolution of the largest vortex in the solar system. The Great Red Spot serves as both a scientific benchmark and a visible marker of Jupiter's atmospheric dynamics. Its position, color, and rotation are monitored continuously. The storm's interactions with neighboring jets and vortices illustrate the complex interplay of convection, rotation, and chemical layering. By studying these interactions over time, scientists can understand the mechanisms that sustain such a large and long-lived storm, offering a window into the physics of giant planets. Measurement of the storm's dimensions shows consistent east-west elongation due to rapid rotation. The north-south width is narrower, constrained by adjacent jet streams and differential rotation. Variations in size over decades demonstrate that while contraction occurs, the overall shape remains roughly oval. Observations of internal circulation reveal rising gas in the center and descending motion along the edges, maintaining a self contained vortex. Spectroscopy provides information on the cloud top chemistry. Specific absorption bands indicate the presence of compounds that contribute to coloration. Variations in cloud height, opacity, and composition explain changes in the reddish hue. Tracking these chemical markers alongside wind measurements allows scientists to correlate physical and chemical changes with observed color shifts. Long term monitoring requires consistent methodology. Observers must account for differences in instruments, viewing angles, and atmospheric seeing. Data from multiple sources are cross referenced to create a continuous record. Time series analysis reveals trends and fluctuations, allowing researchers to distinguish between temporary variations and long term changes. This approach ensures an accurate understanding of the storm's evolution and supports predictions about its future behavior. The Great Red Spot is enormous in size, stretching approximately 16,000 kilometers from east to west. Its north south width is smaller, roughly 12,000 kilometers, giving it a stretched oval appearance. The depth of the storm is difficult to measure directly, but observations suggest that it extends several tens of kilometers below the visible cloud tops. Estimates of volume indicate that it could contain enough gas to encompass multiple Earths, with space inside the vortex occupied by rotating air, clouds, and rising and sinking gases. Despite gradual contraction over time, the storm remains the largest known vortex in the solar system. Wind speeds within the Great Red Spot vary depending on location. The outer edges move fastest, exceeding 400 kilometers per hour, while the interior rotates more slowly. Wind direction is generally counterclockwise in the southern hemisphere, following the Coriolis effect caused by Jupiter's rotation. These winds create strong vorticity, a measure of the local rotation of the gas. The combination of high wind speed, rotational shear, and differential motion across the storm maintains its structure and stability, preventing it from dissipating even under continuous interaction with surrounding atmospheric flows. The vertical structure of the storm is layered. At the top, ammonia clouds form bright features visible in optical wavelengths. Beneath these, layers of ammonium hydrosulfide clouds appear darker, adding to the storm's color and contrast. Even deeper, water clouds may exist, forming at higher pressures and temperatures, though these layers are largely hidden from direct observation. Temperature gradients within the storm indicate that the core is warmer than surrounding regions, consistent with rising gas, bringing heat from deeper in the atmosphere. This high pressure core contributes to the stability and longevity of the vortex. Cloud tops in the Great Red Spot exhibit motion independent of the deeper layers. Observations show that while upper clouds rotate at high speed, deeper motions are slower, creating a vertical shear that can stabilize the storm. Rising gas from lower layers carries heat and material upward, while descending gas along the edges releases heat back into surrounding zones. This circulation allows the storm to maintain energy over long periods. Infrared observations reveal that the storm's center is warmer than adjacent areas, supporting the presence of a high-pressure core. Comparing the Great Red Spot to smaller Jovian storms highlights the differences in scale and dynamics. White ovals and brown ovals, common in Jupiter's southern hemisphere, are significantly smaller, typically a few thousand kilometers across. They rotate more quickly and have shorter lifetimes, often merging with other storms or dissipating within years. The Great Red Spot, in contrast, can persist for centuries. Its size allows it to draw energy from surrounding jet streams, which smaller storms cannot access as effectively. The structure of smaller storms is simpler, with less vertical depth and weaker internal circulation. Measurements of wind speed and direction provide insight into the storm's internal dynamics. Cloud tracking and Doppler imaging allow scientists to calculate rotational velocity at various layers. The outer periphery exhibits the highest velocities, while the center rotates more slowly. The differential rotation within the vortex contributes to vorticity and helps sustain the storm against dissipation. This pattern is similar to hurricanes on Earth, though on a vastly larger scale and without interaction with a solid surface. The depth of the Great Red Spot is also significant. Estimates suggest that the storm extends at least 20 kilometers below the cloud tops, with some models indicating even deeper routes. This depth allows for vertical circulation, where rising gas brings energy from below while cooler air descends along the edges. Thermal gradients are maintained by the balance between internal heat, rising convective currents, and cooling at higher altitudes. These gradients play a role in the color and visibility of clouds, influencing how the storm is observed in different wavelengths. Vorticity, or the measure of rotation, is strongest at the edges of the storm. The rapid movement of gas along the perimeter interacts with surrounding jet streams, stabilizing the vortex. The inner region rotates more slowly, but contributes to the overall energy balance by channeling heat and gas upward. The combination of radial shear, high wind speed, and vertical circulation produces a self-sustaining system capable of persisting over centuries, despite constant turbulence in the surrounding atmosphere. Chemical composition affects the storm's appearance and dynamics. Ammonia, water, and complex hydrocarbons participate in cloud formation at different layers. Rising gas carries these compounds upward, where condensation forms visible clouds. The distribution of chemicals influences color, opacity, and reflectivity. Spectroscopic observations reveal variations in cloud height and composition across the storm, indicating dynamic vertical transport and active chemical processes. The comparison with smaller storms also emphasizes the importance of size in sustaining longevity. Small vortices lack the volume to maintain energy over long periods. They are more easily disrupted by surrounding turbulence or shear zones. In contrast, the Great Red Spot's size allows it to absorb and redistribute energy effectively, interacting with nearby jet streams to maintain coherence. This self-contained system demonstrates how scale and atmospheric conditions combine to produce a persistent feature in a gas giant's turbulent environment. The vertical layering contributes to thermal gradients, which drive convection within the storm. Warm gas rises in the center, while cooler gas descends along the edges. This circulation pattern transfers heat upward and maintains cloud formation at different altitudes. The combination of vertical motion, rotational shear, and chemical layering establishes a stable yet dynamic system. Observations from Juno and Hubble indicate that temperature differences across layers are consistent with energy transfer through convection, supporting the long-term stability of the vortex. Cloud features show variation across the storm. Some regions display dense, well-defined clouds, while others are more diffuse. These differences reflect localized changes in vertical motion, temperature, and chemical concentration. Smaller storms within the Great Red Spot can form and dissolve, contributing to local turbulence. The large size allows these minor disturbances to occur without destabilizing the overall vortex, demonstrating the interplay between scale, rotation, and energy flow. Measurements of rotational patterns also reveal periodic variations. Wind speed along the edges fluctuates slightly over time, while the core remains relatively stable. These oscillations are linked to interactions with surrounding jet streams and smaller vortices, providing a continuous source of energy that reinforces the main storm. Observations indicate that these variations do not significantly alter the storm's overall structure, allowing it to persist across decades. The Great Red Spot's high-pressure core is a defining feature. It maintains vertical stability, preventing the vortex from collapsing under surrounding turbulence. Rising gas from lower layers reinforces the core, while descending gas along the perimeter releases heat back into adjacent belts. The pressure differential between the storm center and surrounding atmosphere drives wind speed, cloud motion, and rotational stability. The core's existence is confirmed by thermal measurements and wind mapping, showing a concentration of energy and rotation that supports long term persistence. Observations from multiple angles have improved understanding of vertical structure. Microwave measurements penetrate cloud tops, revealing deep circulation patterns. Infrared sensors detect temperature differences, confirming the presence of a warm core. High resolution imaging tracks cloud movement, allowing scientists to map wind vectors at multiple levels. These combined measurements provide a three-dimensional view of the storm, showing how vertical circulation, rotational shear, and chemical composition interact to sustain the vortex. The comparison of the Great Red Spot to smaller storms also illustrates the role of planetary rotation. Fast rotation stretches vortices east-west, stabilizes circular motion, and enhances vorticity at the edges. Smaller storms experience similar forces, but cannot achieve the same balance of energy and structure due to limited size. The correlation between rotation, scale, and longevity is evident across Jupiter's atmosphere, demonstrating how physical factors shape storm systems on gas giants. The distinctive red color of the Great Red Spot has long intrigued scientists. The exact cause of the coloration is still under investigation, but several hypotheses focus on the presence of chromophores, molecules that absorb specific wavelengths of light and produce visible color. Observations suggest that these compounds exist within the upper cloud layers of the storm, particularly in the ammonia cloud deck. The reddish hue is concentrated in certain regions, with variations in tone and intensity reflecting differences in chemical composition and vertical mixing. Ammonia plays a key role in cloud formation and chemical reactions. When combined with other compounds, such as acetylene or phosphorus-containing molecules, ammonia can participate in reactions that produce colored aerosols. These aerosols absorb sunlight at specific wavelengths, creating the red coloration observed from Earth and spacecraft. Laboratory simulations of ammonia mixed with trace chemicals under conditions similar to Jupiter's upper atmosphere produce reddish-brown hues, supporting the hypothesis that ammonia-related chemistry contributes to the color. Acetylene, a simple hydrocarbon, is formed in Jupiter's stratosphere through photochemical reactions driven by ultraviolet sunlight. This compound can combine with other trace molecules to form more complex hydrocarbons, which in turn may contribute to visible color in cloud particles. The distribution of acetylene and its derivatives is influenced by vertical mixing, circulation patterns, and exposure to sunlight. As gas rises into the storm, chemical reactions may alter pigment concentration, producing variations in hue and intensity. Across the vortex, phosphorus compounds are another potential source of coloration. Phosphine, present in small quantities in Jupiter's atmosphere, can undergo chemical transformations in the presence of ultraviolet light or other reactive molecules. These reactions may create phosphorus-bearing aerosols with reddish tones. Observations using infrared and ultraviolet spectroscopy detect spectral features consistent with phosphorus compounds, suggesting that these molecules contribute to the chromophore population within the storm. Complex hydrocarbons formed from methane and other small molecules also influence coloration. Methane absorbs sunlight, especially in the ultraviolet range, and participates in reactions that generate larger, more complex molecules. These molecules can condense into particles that scatter light differently depending on size and composition. Variations in cloud particle size and chemical makeup produce subtle shifts in observed color, resulting in the patchy, uneven red tones seen in high-resolution images. Seasonal and solar influences affect pigment formation as well. Ultraviolet light from the sun drives many photochemical reactions, producing colored compounds in the upper layers of the storm. Although Jupiter's seasons are mild due to its small axial tilt, slight variations in solar angle and intensity can influence the rate of chemical production. Over time, these factors may contribute to gradual changes in hue, resulting in observable differences in red intensity across years or decades. Spectroscopic data provide insight into the chemical composition of the Great Red Spot. Instruments on Hubble, Juno, and ground based telescopes capture reflected sunlight and emitted thermal radiation across multiple wavelengths. Analysis of absorption and emission features allows scientists to identify specific molecules and estimate their abundance. Observations confirm the presence of ammonia, methane, and minor hydrocarbons, while also indicating phosphorus and sulfur bearing species. The combination of these compounds produces the overall coloration observed. Chemical modeling complements observations. Simulations of Jupiter's atmosphere account for temperature, pressure, sunlight exposure, and known chemical pathways. These models predict how ammonia, hydrocarbons, and phosphorus compounds interact to form chromophores. By comparing modeled spectra with actual observations, researchers can narrow down which molecules are likely responsible for red coloration. Models suggest that a mixture of chemicals, rather than a single compound, is responsible for the diverse red tones seen across the storm. The vertical distribution of chemicals also affects visible color. Chromophores concentrated near the top of ammonia clouds are more effective at absorbing and scattering sunlight, producing stronger coloration. Lower concentrations and deeper cloud layers contribute less to the visible red, though they may influence infrared signatures. Upward convection within the Great Red Spot transports chemicals from lower levels, while turbulent mixing redistributes aerosols horizontally, producing patchiness and streaks in color. Over decades of observation, the red intensity has fluctuated. Some measurements indicate periods when the storm appeared darker and more saturated, while other times it seemed lighter or paler. These changes correspond to variations in cloud composition, vertical mixing, and perhaps minor shifts in photochemical production rates. Solar activity and the slight seasonal cycle may modulate the photochemical reactions that create chromophores, influencing the storm's appearance over time. High-resolution imaging from Juno shows localized differences in color within the storm. Small vortices and plumes within the Great Red Spot exhibit slightly different shades of red, brown, or orange. These variations likely reflect localized chemical concentrations, temperature differences, or cloud particle sizes. The combination of vertical circulation, horizontal turbulence, and chemical interactions produces the detailed and uneven coloration observed. Laboratory experiments under conditions simulating Jupiter's atmosphere have replicated red pigments using mixtures of ammonia, acetylene, and phosphorus compounds. When subjected to ultraviolet light, these mixtures form reddish particles that float in a simulated gas layer, supporting the hypothesis that similar processes occur in the storm. These results indicate that the coloration is a product of chemical complexity and photochemistry rather than a single pigment. Spectroscopy also reveals absorption features that cannot be explained solely by ammonia or water. Weak bands in the visible and near infrared correspond to complex hydrocarbon or phosphorus-bearing molecules. Analysis of these bands helps constrain the possible chemical compositions responsible for red coloration by combining observational data, chemical models, and laboratory experiments. Scientists can narrow the list of candidate chromophores to those most consistent with the measured properties of the storm. The observed variations in red intensity also correlate with cloud thickness and altitude. Areas with thicker ammonia clouds tend to scatter more sunlight, producing brighter or more intense red hues. In regions where clouds are thinner, the color may appear muted. Infrared imaging confirms that cloud height and particle density influence the visible spectrum, linking physical cloud properties to observed coloration. Photochemistry is central to pigment formation. Solar ultraviolet photons break molecular bonds, creating reactive species that combine to form colored aerosols. The rate of photochemical reactions depends on sunlight exposure, atmospheric composition, and the presence of reactive trace gases. In the upper layers of the storm, repeated cycles of photochemistry and vertical transport ensure a continual supply of chromophores, sustaining the red appearance over time. The balance of chemical production, vertical mixing, and cloud formation determines both the intensity and distribution of color. Rising plumes carry freshly produced chromophores to higher altitudes, where they condense into cloud particles. Turbulence spreads these particles horizontally, creating streaks, patches, and gradients of color. The interplay of chemistry and atmospheric motion results in the complex and changing red tones characteristic of the Great Red Spot. Seasonal and solar factors, while subtle on Jupiter, can modulate chemical activity. Changes in solar ultraviolet flux affect photochemical rates, while variations in atmospheric circulation influence how pigments are transported. Over years or decades, these factors contribute to slow changes in the overall red intensity, supporting long-term trends observed in historical and modern records. Chemical composition also influences thermal properties. Chromophore-rich clouds absorb sunlight differently than ammonia-dominated clouds, affecting temperature distribution within the storm. These thermal differences contribute to convection, influencing vertical motion and cloud development. In this way, color and dynamics are interlinked, with chemical composition affecting both appearance and atmospheric behavior. Observations using spectrometers capable of detecting ultraviolet, visible, and infrared light reveal the distribution of key molecules. Ammonia, acetylene, phosphorus compounds, and complex hydrocarbons are detected at varying altitudes. These data confirm that multiple chemicals act together to produce the red coloration, supporting the idea that the appearance is a result of layered chemistry and atmospheric mixing rather than a single pigment source. The continuous monitoring of the Great Red Spot allows for correlation between chemical data and visual observations. Bright regions often correspond with higher concentrations of chromophores, while darker areas may indicate depletion or dilution. Vertical mixing and local turbulence contribute to the patchy distribution of pigments, producing the detailed variations in red, brown, and orange hues seen in spacecraft images. Jupiter generates more heat than it receives from the Sun. This internal heat comes from two primary sources. One source is residual energy left over from the planet's formation. As the planet formed from gas and dust, gravitational energy converted to heat, which remains trapped inside. The second source is ongoing gravitational contraction. Jupiter slowly shrinks under its own gravity, compressing material in the interior. This compression releases energy as heat, adding to the internal temperature. Together, these processes maintain a warm interior that drives atmospheric motion. Heat moves outward from the interior through convection. Hot gas rises because it is less dense than the surrounding material. As gas rises, it expands and cools, carrying energy toward the upper layers of the atmosphere. Cooler gas sinks to replace it, creating a continuous circulation. These convective cells are not uniform. They vary in size and intensity depending on local conditions. In regions where rising gas meets horizontal jet streams, it can form vortices that develop into storms, including smaller ovals and larger features like the Great Red Spot. The influence of solar radiation on Jupiter's atmosphere is comparatively small. While sunlight contributes to cloud heating and photochemical reactions in the upper atmosphere, the energy it provides is minor compared to the internal heat from convection. The interior heat drives the main circulation, producing the high-speed winds, turbulent vortices, and vertical motion that characterize the planet. Seasonal variations in sunlight have little effect on overall storm formation because internal processes dominate energy transport. Deep convection interacts with the upper cloud layers. Rising gas from the interior pushes through layers of ammonia, ammonium hydrosulfide, and water clouds. As gas ascends, It carries heat and chemical compounds upward. Condensation occurs at specific altitudes, forming clouds that reflect sunlight and contribute to the visible appearance of storms. The vertical motion also influences color and composition, as compounds from lower layers mix with material in the upper atmosphere. Convection affects storm intensity and stability. Regions with strong upward motion can produce large, long lived vortices. Energy from rising gas feeds the storm's rotation, while descending gas along the periphery releases heat back into the surrounding atmosphere. This exchange sustains vortices over long periods, even amid surrounding turbulence. Smaller storms follow similar principles, but often lack the energy or scale to maintain stability over decades. Temperature gradients between the interior and the upper atmosphere control the strength of convective motion. Deeper layers are warmer due to trapped heat, while higher layers are cooler. This difference in temperature drives buoyancy, producing rising and sinking gas. The contrast also affects cloud formation, as gas cools while ascending and condenses into clouds. Thermal gradients are particularly important in maintaining the high pressure core of the Great Red Spot. Internal heat contributes to the redistribution of chemical species. Rising gas carries ammonia, water vapor, and trace hydrocarbons to higher altitudes. These compounds participate in cloud formation and chemical reactions, including those that produce coloration in storms. Descending gas returns material to lower layers, completing a circulation cycle that mixes the atmosphere vertically. This dynamic ensures that storms remain chemically and thermally active over long periods. The interaction between deep convection and jet streams shapes the planet's atmospheric bands. Rising gas encounters horizontal winds that shear the material, producing elongated vortices and bands. This process explains the distinct, striped appearance of Jupiter. Energy from convection feeds into these jets, maintaining their speed and stability. At the same time, turbulence generated by interacting currents produces smaller vortices, which merge or dissipate over time. Observations indicate that energy from the interior sustains most large storms. Infrared imaging reveals hotspots where heat emerges from below. These hotspots correlate with regions of rising gas that supply energy to the overlying clouds. Energy transfer is not uniform. Some areas receive more heat than others, producing variability in storm size, intensity, and color. This uneven distribution contributes to the patchiness and motion observed in vortices. Convection also influences the depth of storms. Gas rising from the interior carries momentum and energy, extending vertical circulation through multiple cloud layers. Some vortices penetrate deep into the atmosphere, while others remain confined to upper levels. The depth of a storm determines its energy content, rotational strength, and ability to persist over decades. Larger storms draw energy from deeper layers, explaining why the Great Red Spot can survive for centuries, while smaller storms dissipate more quickly. The balance between internal heat and external sunlight determines overall atmospheric behavior. While sunlight affects cloud tops and drives photochemistry, the interior heat dominates the energy budget. Vertical motion, powered by internal heat, produces the main convection cells, which drive jet streams and vortices. This balance explains why Jupiter's atmosphere exhibits strong storms year-round, with limited seasonal variation. Heat from gravitational contraction also affects atmospheric composition. Rising warm gas carries trace compounds upward, where they interact with ammonia, methane, and water vapor. These interactions influence cloud chemistry and coloration. The continuous supply of energy from below ensures that chemical processes remain active, maintaining cloud patterns, chromophores, and storm coloration. Convective cells vary in scale across Jupiter. Small cells may be only a few hundred kilometers wide, while large cells span thousands of kilometers. The size of a cell influences its ability to generate vortices. Large convective regions produce more substantial energy flux, creating conditions for long lived storms. Small convective regions generate localized turbulence, forming short lived ovals or small vortices within bands. The interaction between rising and descending gas forms high pressure cores in large storms. Warm gas rises in the center, generating low density regions that create circulation. Surrounding gas descends, balancing pressure and returning heat to adjacent layers. This pattern stabilizes the vortex and maintains its structure, allowing energy from the interior to circulate efficiently within the storm. Observational data support these dynamics. Infrared measurements from Juno show regions of enhanced heat flux corresponding to storm centers. Microwave instruments reveal the depth of rising gas and its effect on cloud formation. Wind tracking confirms that energy from deep convection feeds rotation, maintaining vorticity and horizontal shear. The combination of these observations provides a complete picture of how internal heat drives atmospheric activity. Energy from convection also redistributes chemical species horizontally. Rising gas carries compounds to cloud tops, while lateral winds spread material across belts and zones. This process maintains chemical gradients, contributes to coloration, and supports the formation of new vortices. The dynamic interaction of vertical and horizontal transport ensures that Jupiter's atmosphere remains complex and active over long periods. The balance between internal heat and turbulence is critical. Excess energy can destabilize storms, while insufficient energy allows vortices to weaken. Convection regulates this balance by supplying heat in a controlled, distributed manner. Large storms like the Great Red Spot benefit from this steady supply, while smaller storms are more sensitive to fluctuations in convective input. Solar radiation plays a minor but measurable role. Photochemical reactions at the cloud tops depend on sunlight, producing compounds that influence coloration and cloud reflectivity. Sunlight also affects temperature at the highest layers, slightly modulating convection and cloud brightness. However, the energy contribution is small relative to heat from internal sources, so its impact on storm formation and dynamics is limited. The Great Red Spot exists within a dynamic and layered atmosphere. Surrounding jet streams influence the storm's shape and motion. These bands of high speed wind flow parallel to lines of latitude and alternate in direction. The interaction between the storm and these jets stretches the vortex east west and stabilizes its rotation. When the storm drifts into a faster moving jet, it can be elongated or slightly distorted, while slower surrounding winds allow the vortex to contract and maintain its oval form. Smaller vortices that form nearby are often absorbed into the Great Red Spot. Those smaller storms, sometimes white or brown ovals, approach the main vortex along wind patterns and can merge with it. During merging, energy and momentum are transferred, adding to the rotation and sustaining the storm's intensity. Some smaller vortices are deflected around the edges of the Great Red Spot, their paths altered by strong peripheral winds. These interactions illustrate how energy and motion are redistributed across Jupiter's atmosphere. Long-range transport of energy occurs through both convection and horizontal flow. The storm draws energy from distant regions via jet streams, absorbing momentum from fast-moving gas. Turbulent eddies form where jets meet, generating small waves that propagate toward the storm. This movement contributes to the rotational strength of the vortex and allows the storm to maintain energy levels over decades. Even distant storms can influence the Great Red Spot if they transfer energy through connecting currents. Turbulence in the surrounding atmosphere is a constant feature. Wind shears, small vortices, and undulating waves create a complex environment around the storm. High-resolution images show chaotic patterns of clouds bending and twisting as they approach the vortex. These patterns reveal the interaction of fast-moving gas with the storm's outer edges, where momentum is transferred and dissipated. The turbulence also produces localized regions of vertical motion, where gas rises or sinks as a result of collisions between currents. Wave propagation occurs within and around the storm. Atmospheric waves, including Rossby waves and gravity waves, carry energy across long distances. Waves generated by smaller storms or jet stream instabilities travel toward the Great Red Spot, altering the distribution of pressure and wind speed. These waves can amplify rotation or produce temporary distortions in the storm's shape. Continuous monitoring shows that waves contribute to the persistence of smaller features along the storm's edge. The absorption of smaller storms enhances the energy of the Great Red Spot. As vortices are drawn in and merged, kinetic energy is transferred to the main vortex. This process increases wind speed along the periphery and sustains internal circulation. Observations indicate that mergers occur periodically, contributing to fluctuations in rotation and minor variations in shape. Deflected vortices continue to interact, sometimes forming chains or bands that influence the surrounding atmosphere. Peripheral winds act as barriers, guiding nearby storms along specific paths. Gas moving toward the storm encounters high-speed flow along the outer edge, which can bend its trajectory. In some cases, vortices partially merge before being carried away by the jet stream, redistributing energy without full absorption. These interactions reveal the complexity of momentum exchange in a highly stratified atmosphere, where vertical and horizontal motion are interconnected. Turbulence patterns vary with altitude. Upper cloud layers display rapid motion and chaotic mixing, while deeper layers show more gradual, laminar flow. Waves propagating through the atmosphere affect multiple layers simultaneously, producing correlated motion in clouds at different heights. Observations from Juno and Hubble show that disturbances in one region can influence storm behavior at a distance, indicating a highly coupled system of energy transfer. Long-range interactions also affect the distributions of chemical compounds. Rising gas from smaller storms carries ammonia, water, and hydrocarbons that mix with the edge of the Great Red Spot. This mixing can alter coloration, cloud density, and chemical composition locally. Deflected or merged storms introduce fresh material, sustaining cloud formation and contributing to variations in appearance across the vortex. The Great Red Spot's rotation interacts with wave systems in the surrounding atmosphere. Waves can amplify wind speed along the outer edges, creating fluctuations in vorticity. These fluctuations are often temporary, but contribute to minor variations in shape, such as bulges or indentations along the perimeter. The continuous exchange of energy between waves, jets, and smaller vortices maintains a dynamic balance that preserves the storm's overall structure. Observations reveal that smaller vortices sometimes form in the wake of the Great Red Spot. These features can be carried along by the storm's rotation or interact with adjacent jet streams. The emergence of these secondary vortices demonstrates how momentum and energy are redistributed, producing local turbulence while leaving the main vortex largely stable. Monitoring these events helps scientists understand the flow of energy and the resilience of large-scale storms. Interactions between the storm and surrounding jet streams also influence its longevity. The storm extracts energy from faster-moving bands and transfers excess momentum into slower regions. This exchange regulates the storm's rotational speed and contributes to a stable energy balance. Without these interactions, the vortex might gradually lose energy and weaken over decades. Horizontal transport of energy extends across thousands of kilometers. Currents originating in distant belts or smaller storms can influence cloud motion and wind speed within the Great Red Spot. Momentum transported along jet streams reinforces the storm's rotation, while turbulence disperses some energy, preventing overaccumulation in one region. This balance between input and dissipation contributes to long-term stability. High-resolution imaging shows detailed turbulence at the edges of the storm. Cloud filaments stretch and twist, forming small scale vortices and wave patterns. These structures reveal complex interactions between rotational motion, peripheral winds, and nearby storms. The turbulent boundary absorbs, deflects, or incorporates energy from passing features, sustaining circulation without destabilizing the main vortex. The movement of smaller vortices around the Great Red Spot illustrates momentum transfer. Some vortices spiral inward and merge, enhancing rotation. Others are carried along the periphery, gradually losing energy while creating turbulence. These processes demonstrate how large scale storms can interact with surrounding features while maintaining their core structure and energy. Atmospheric waves propagate both vertically and horizontally. Gravity waves move energy from lower layers to the upper atmosphere, affecting cloud formation and wind speed. Rossby waves, influenced by Jupiter's rotation, travel along latitudinal bands and alter pressure fields, which can temporarily distort the shape of the Great Red Spot. Continuous observation shows that wave activity is a critical component of energy redistribution in Jupiter's atmosphere. The interaction with surrounding atmosphere also influences cloud patterns. Rising gas from nearby turbulence can inject ammonia or other compounds into the edges of the storm. Descending flows along the periphery remove heat and momentum, producing local variations in cloud density and temperature. These processes contribute to the detailed structure observed in high resolution images, including streaks, swirls, and filamentary patterns. Observations indicate that long range transport of energy connects the Great Red Spot with storms located thousands of kilometers away. Wind streams and wave propagation carry momentum across belts and zones. Energy arriving from distant features can increase rotation speed, influence vorticity, or alter turbulence patterns at the storm's edge. The continuous flow of energy from the surrounding atmosphere is essential to sustaining the vortex over centuries. The Great Red Spot has persisted for centuries, surviving far longer than typical storms observed on other planets. Its longevity is supported by multiple mechanisms. The storm's large size allows it to draw energy from surrounding jet streams, absorbing momentum and stabilizing its rotation. Internal heat from deep convection supplies energy from below, sustaining vertical circulation and replenishing the storm's intensity over time. The combination of energy from above and below produces a self-sustaining system capable of enduring despite surrounding turbulence. Historical records show that the storm has changed in shape and size over the centuries. Early observations depict the Great Red Spot as larger than it appears today. Its length has gradually contracted, with a reduction in east-west extent, while its north-south width has fluctuated less noticeably. Shape changes include occasional elongation, rounding, or slight distortion caused by interactions with nearby jets and smaller vortices. Despite these variations, the core rotation remains strong, maintaining the storm's essential structure. Intensity variations are also observed. Wind speeds along the periphery fluctuate with time, influenced by mergers with smaller vortices or interactions with surrounding jets. Measurements over decades indicate periods when the storm appears darker, suggesting higher chromophore concentration, and times when it becomes paler. These changes correspond to variations in cloud composition, vertical motion, and energy influx from convection and surrounding winds. Jupiter's rapid rotation plays a critical role in the stability of the Great Red Spot. The planet completes a rotation roughly every 10 hours, producing strong Coriolis forces. These forces deflect moving gas, encouraging circular motion and reinforcing vorticity along the storm's edges. The rapid spin also stretches the vortex east-west, contributing to its elongated oval shape. Without this rotation, the storm would likely disperse more quickly under the influence of turbulence in the surrounding atmosphere. Comparisons with storms on other planets highlight the exceptional nature of the Great Red Spot. On Earth, the largest hurricanes rarely persist for more than a few weeks, limited by energy supply and interaction with land and oceans. On Saturn, large storms form and dissipate over months or a few years, influenced by planetary rotation and atmospheric conditions. In contrast, Jupiter's combination of size, deep convection, and rapid rotation enables the Great Red Spot to maintain coherence for centuries, making it unique in the solar system. Observations indicate that the storm's shrinkage has accelerated in recent decades. High resolution imaging shows a gradual reduction in length from historical estimates. The north south width has remained more stable, suggesting that contraction occurs primarily along the east west axis. Despite this reduction, the storm retains sufficient size to interact strongly with jet streams, ensuring that rotational energy and momentum continue to be replenished. The internal dynamics of the storm contribute to its persistence. Rising gas carries heat and chemicals from lower layers into the vortex, while descending gas along the edges balances pressure and releases energy into the surrounding atmosphere. This vertical circulation maintains cloud formation, chromophore distribution, and rotational stability. The depth of the vortex allows the storm to access energy unavailable to smaller storms, which helps explain its exceptional lifetime. Mergers with smaller vortices further reinforce longevity. When minor storms approach and are absorbed, they transfer kinetic energy to the main vortex. This process increases wind speed at the edges, strengthens rotation, and sustains the high pressure core. Even deflected vortices contribute to turbulence around the periphery, maintaining dynamic balance without destabilizing the storm. Such interactions create a continuous cycle of energy input, critical for survival over centuries. Long-term monitoring shows subtle changes in rotational pattern. Wind speeds along the outer bands vary over time, occasionally slowing or accelerating slightly. The inner core remains more stable, preserving the storm's overall structure. These fluctuations may correspond to shifts in surrounding jet streams, minor wave propagation, or chemical changes in cloud composition. Despite these variations, the storm's internal circulation continues to function effectively. Thermal properties influence temporal evolution. Heat from deep convection drives upward motion, sustaining cloud formation and vertical circulation. Temperature gradients between the core and surrounding atmosphere regulate buoyancy and wind speed, contributing to stability. Variations in energy flux, due to changes in internal heat or interactions with the surrounding atmosphere, can lead to observable differences in cloud density and rotation rate. Observations over centuries suggest that the storm has maintained a roughly consistent rotational period. High-speed winds along the periphery remain within predictable ranges, while internal motion continues to circulate efficiently. These long-term trends indicate a stable energy balance, where input from convection and jet streams compensates for energy lost to turbulence and wave propagation. Color variations over time also reflect chemical and physical evolution. Chromophore concentration changes as gases from below mix with cloud layers and as photochemical reactions proceed under sunlight. Darker periods correspond with higher pigment concentration, while lighter periods may indicate dilution or reduced production. These variations are minor compared to the overall persistence of the vortex, but provide insight into temporal changes in chemical composition and cloud dynamics. Shape changes are influenced by interactions with the surrounding atmosphere. Elongation, or rounding or bulging, occurs when jet streams vary in speed or direction, or when nearby vortices exert force on the periphery. Despite these modifications, the central rotation remains stable, indicating a decoupling of minor distortions from the core structure. This decoupling is essential to the storm's continued existence. The comparison with smaller storms on Jupiter further emphasizes the significance of scale. Smaller vortices dissipate over months or years because they cannot draw sufficient energy from surrounding jets or access deep convective heat. The Great Red Spot's size allows it to interact effectively with its environment, sustaining motion and circulation even when individual features or peripheral clouds fluctuate. Observations indicate that minor contractions and expansions in size have occurred over decades. While east west length decreases gradually, occasional widening events may result from interactions with jet streams or mergers with smaller storms. These changes do not compromise the storm's integrity, as energy transfer and rotational stability continue to function. The Great Red Spot provides a unique window into planetary atmospheres and the physics of giant storms. Its scale, longevity, and structure make it an ideal subject for study, offering insights that cannot be obtained from smaller or short lived storms. Researchers examine the vortex to understand how energy, momentum, and chemical composition interact over long periods. Observations reveal how internal heat, rotation, and atmospheric turbulence combine to sustain a large scale storm, providing a model for similar phenomena in other planetary systems. Studying the Great Red Spot informs our understanding of jet stream behavior. The interaction between the vortex and surrounding bands demonstrates how energy is transferred between large and small scale flows. By analyzing wind speeds from vorticity and circulation patterns, scientists can develop models of atmospheric dynamics that apply to other giant planets. These models help explain why storms form, how they evolve, and what factors contribute to their longevity, offering a broader framework for comparative planetary meteorology. The storm also provides data on chemical processes in extreme atmospheres. By observing cloud composition, chromophore distribution, and photochemical reactions, researchers gain insight into how molecules interact under high pressure, low sunlight, and rapid motion. The interplay between ammonia, water, hydrocarbons, and phosphorus compounds illustrates the complexity of chemical transport in a deep atmosphere. These findings improve the interpretation of spectroscopic data from other gas giants, both in our solar system and beyond. Insights gained from the Great Red Spot extend to exoplanet research. Many giant exoplanets, particularly those close to their stars, exhibit strong atmospheric circulation, high winds, and large scale vortices. By understanding Jupiter's storm physics, scientists can better model the atmospheres of these distant worlds. Observations of color, temperature gradients, and vertical cloud structure on Jupiter provide a baseline for interpreting similar data from exoplanets detected through spectroscopy or transit studies. The storm demonstrates the role of rotation in atmospheric stability. Rapid planetary rotation, as on Jupiter, produces Coriolis forces that maintain large vortices. Comparing these dynamics to slower rotating planets helps explain the variety of storm behavior observed across the solar system. For example, Earth's hurricanes are short lived and limited in size, while Jupiter's rapid spin enables a single vortex to persist for centuries. This comparison highlights the importance of rotation in determining storm scale, shape, and stability. Future missions aim to deepen understanding of the Great Red Spot. Instruments capable of high-resolution imaging, infrared mapping, and microwave probing will measure wind velocities, temperature, and chemical composition more precisely. Continued Juno observations provide close-up data on vertical structure, while Earth-based telescopes supplement long-term monitoring. These combined strategies ensure that the storm's dynamics and chemical evolution are tracked over time, enabling more accurate models and predictions. Researchers also plan to investigate wave interactions within and around the storm. Understanding how Rossby waves, gravity waves, and turbulence contribute to its energy distribution will clarify the mechanisms that stabilize the vortex. Long-term tracking of smaller vortices and peripheral turbulence provides insight into energy transfer and the coupling between the storm and the surrounding atmosphere. Observations over decades allow scientists to correlate these effects with changes in color, wind speed, and cloud structure. Advances in laboratory simulations and chemical modeling complement observational data. Experiments reproducing Jupiter like pressures, temperatures, and chemical mixtures allow researchers to study pigment formation, cloud microphysics, and reaction rates. Chemical models predict how ammonia, phosphorus, hydrocarbons, and water vapor interact, while experimental data verify these predictions. Together, modeling and laboratory work refine understanding of the processes responsible for coloration, cloud behavior, and storm stability. The Great Red Spot also provides a test case for numerical weather models applied to giant planets. High resolution simulations can reproduce the observed bands, vortices, and long term evolution. Comparing simulation outputs with spacecraft observations enables validation of physical assumptions, including convective heat transfer, energy input, and rotational effects. These models help predict future evolution, assess potential shrinkage or intensification, and explore scenarios of storm interactions with the surrounding atmosphere. Despite extensive study, many open questions remain. The exact mechanisms controlling the storm's ultimate longevity are not fully understood. The processes governing color variations and chromophore production continue to be investigated. Additionally, the internal structure beneath visible cloud layers remains partially hidden, requiring inference from indirect measurements, such as gravitational data or microwave emissions. Understanding these aspects is essential to fully grasp the physics of giant storms. Long term, monitoring remains crucial. Continuous observations allow scientists to detect subtle changes in wind speed, rotation, and shape. These measurements provide context for chemical and thermal evolution and help identify the role of external influences, such as solar activity or interactions with smaller vortices. By maintaining a consistent observational record, researchers can track trends and refine models of storm dynamics and atmospheric behavior. The Great Red Spot serves as a benchmark for comparative planetology. Its persistence and scale highlight the differences between giant planets and terrestrial worlds. Studying its energy balance, chemical processes, and interaction with surrounding atmospheric structures provides a reference point for understanding storms in diverse environments, both within our solar system and among exoplanets. Finally, ongoing study combines multiple approaches: spacecraft observations, Earth based imaging, spectroscopic analysis, laboratory, simulations, and numerical modeling work together to build a comprehensive picture. This integrated approach allows scientists to explore how internal heat, solar input, rotation, chemical composition, and atmospheric dynamics interact to sustain one of the solar system's most extraordinary storms. In summary, the Great Red Spot is a natural laboratory for understanding planetary atmospheres, storm physics, and chemical processes. Observations and models provide detailed knowledge of energy transfer, rotation effects, cloud formation, and chromophore chemistry. Comparisons with other planets highlight the influence of size and rotation on storm longevity. Future missions and continued monitoring promise to refine this understanding, answering remaining questions about one of the solar system's most persistent and remarkable features.